welcome back. So let's hit it off from where we left off. So let's head over to the fourth lecture, DC machines. So remember we had looked at, in the last lecture, we had looked at a coil of wire, had looked at what happens with a coil of wire once we apply a voltage across its terminals. We labeled them AB, and we looked at the way the current moves. The way the current moves in combination with the way the coil has been wound, that completely gave us how the coil of wire is going to create its magnetic fields, how it ends up becoming an electromagnet, right? So this happened to be the south, that was the north. So if we flipped the polarity, if we were to flip the polarity of the supply voltage, thereby reversing the direction of the current, this time round, the current goes that way, comes back down, up, down, up, down, up, up, down, up, down, up, down. So now the polarity flips all together. That one becomes the north, that one becomes the south. So we realize that this is nothing more than a magnet, like any other magnet, right? Like so. And it had properties of a magnet with one extra ability, the ability to control parameters of a magnet. Like parameters like the field strength, where we could control the current I, the current through that coil, So this, remember, the magnetic field strength is proportional to the number of turns in the coil, the current through it, and other parameters like the length or the dimensions. It's also proportional to the dimensions of the coil, like the area. So we had the ability to control these parameters. So we could easily place a resistive load, a variable resistor, in series with the coil, whereby now we can control the current I through the coil, thereby controlling the properties. So we can even now control the orientation of the magnet, which side is the north pole, which side is the south pole, by simply flipping the polarity of the supply voltage to the coil. So that was very important. There is one thing before we shift over to today's lecture, the content of today's lecture. There is something else I want to discuss. How do we strengthen the magnetic field around that coil further? So this is how we will do it. Okay. This is how we would dare to do it. All right. Let's say that's our coil with that polarity. So that means the current I is flowing in that direction with a bottom-up configuration. bottom up configuration, then all the way back to the negative terminal of the source. So if we are to make the magnet stronger, we could easily add what we call a core. So what we call a core, right? What we call a core. So a core is nothing but a good magnetic material like iron. You could get like an iron bar, insert it into the space between the coils, right? And these coils are electrically isolated from each other. So with a thin insulation on top, or call it enamel. All right. So by doing this, this concentrates the magnetic fields that are moving along the axis of the magnet, right? So this will be our south and that will be our north. Very important. So from now on, everything you're yet to see, everything we are yet to cover, be it the construction, real world construction of a DC machine, be it a generator or a motor, it is to essentially have the following: real world construction of a DC machine will require us to have that machine built in a way that it is efficient. Efficient how? We must have an efficient electrical circuit. We must have an efficient magnetic circuit. Very important. So for the magnetic circuit, it's all about how the magnetic flux is being directed, right? How the magnetic flux is being directed and concentrated, right? Concentrated right into the electromagnet. So instead of having like a good portion of the magnetic fields stray off into air, and air is a magnetic insulator. Air is a good magnetic insulator, and it's not a good magnetic conductor. So we need to have a sound and efficient magnetic circuit, thereby a good flow of flux through different parts of the machine. So this will be executed with a good and efficient design of what we've called the core. So after having an efficient electrical circuit, we must have an efficient magnetic circuit where we have good flow of magnetic flux through paths we have pre-planned. All right. So the other is to have an efficient mechanical system, one that can efficiently convert electrical energy to rotational mechanical energy. So one that can have efficient electrical circuit, efficient magnetic circuit, and an efficient mechanical system. So we've seen that we have to juggle the basics. If we are to build, let's say, the armature winding of a DC motor, you get the point? If we are to build the armature of a DC generator, we must combine these basics to have an efficient and real-world construction of a DC machine. But before we go there, let's get over to one last principle or a few, let's just have two principles, right? So that is the motor effect and the basic generator. All right, now let's look at what we call the basic motor effect. Let's imagine a situation, right, where we have a bar magnet, one side of it, let's say the north, directly facing the opposite side of another magnet, which is the south pole. And in between, we happen to be having magnetic fields stretching like so. Let me draw it in 3D space. All right, let's say we have a conductor situated like so in the magnetic field of that pole pair, right? So let's say we apply a positive voltage to point A and a negative to point B. So let's call this side P, D, E, K. All right. So we are going to have the current flow I through that loop. It's going to be the same current I, and that current is going to shift direction the moment it gets to the side EK. Through PD, it's going like that. So let's look at something interesting. That is what we call the left hand rule. So the left hand rule, this is a rule we use to determine what happens to a coil of wire situated in a uniform magnetic field like so, with it carrying current like that. We know it will generate a magnetic field around itself, right? So that magnetic field is going to interact with the already existing magnetic field, and a force is going to act on this side of the loop and that side of the loop, but not the other side between D and K. We will see why. Why not? So we are going to look at two things actually at the same time. The other principle is the Lorentz force. The Lorentz force. So the Lorentz force is a force exerted or experienced by a clean piece of wire carrying current, right, situated in a uniform magnetic field. So that magnetic field is going to exert that force, a force on that conductor. That the direction of that force is going to be determined by the left hand rule, or what we know as the Fleming's left hand rule. So how does it apply? So we stretch out our left hand with the thumb, the first finger and the second finger all at right angles. So we align the first finger to face the direction of the field. So that is going to be the direction of the field because I'm aligning it with the existing field I happen to be having. So the second finger is going to align with maintaining the orientation of the first finger with the field. So that one must orient, the second finger must orient itself with the direction of the current. So the thumb now gives away the direction of the force exerted, the Lorentz force exerted on that conductor. So with that in mind, that means this conductor is going to experience a downward force. Let me call it F1. All right. Let's look at what happens to the other side, because the current has reversed directions around the loop. So with the other side, let's apply the Fleming's left-hand rule. So what are we going to have? So this is what we're going to have. The first finger is going to align itself with the direction of the field. That's nice. That side. The second is now with the direction of the current, like usual, but maintaining the first finger's orientation. So now the thumb completely tells us that the force or the thrust is going to be upwards. So I'll draw it like so. It is also F1, equal and opposite in magnitude. So the loop PDKE is going to experience a rotating force. In this case, it is in the anti-clockwise direction. So the Lorentz force is one that is exerted on a current carrying conductor situated in a uniform magnetic field. So with the Fleming's left-hand rule, we can determine the direction of rotation or the force, direction of the force exerted on that current carrying conductor. So ladies and gentlemen, this is what, in short, what we call a single loop. This is what we call a single loop DC motor. Single loop DC motor. Very, very important. Now, what if we flip? What if, let me play out another scenario. What if now this time round that's the positive and that's the negative? That means the current reverses direction. So does the force, because the field is the same. So this force now is going to go upwards, right? Call it F1. And to this side, we're going to have a downward and equal force called F1. So now the machine or the loop rotates in that sense. So you have a clockwise rotation. That is the basic, that's the basic generic description of a motor. So what we call the motor action or the motor effect. That's what we call the motor effect. That's what we call the motor effect. So if we want now to strengthen the size of that force, so we still have, there is a formula that completely describes the relationship between this force and the magnetic field strength B and the current I flowing through. Current I flowing through that conductor and the length of the side that is experiencing the force. So let's say the length between EK or PD is capital L, then times the sine of the angle of inclination between that side and the field, that side that is experiencing the force and the force field. So sine theta, that force is denoted by Bill, so let me call it F1, Bill sine theta. So if the conductor is at right angles, is at the current, the conductor experiencing the force is at right angles with the field, F1 is simply given as BIL. So B is in Teslas, I is in amps, L is in meters. The magnetic field strength is in Teslas. So that is how it is. So now let's see why dk experiences zero force, right? So force between dk, let me denote it like that, is equal to B. The same current is going to flow through it. Then whatever its L, let's say the length is L dk, I'm calling it dk, yes. Then times sine. Since it's now horizontal parallel to the magnetic field, the angle between it and the magnetic field is 0. The sine of 0 is 0, so the whole thing is 0 newtons. That is why this side never experiences that force. But since it is coupled with, physically coupled with the other sides of the loop, it will move along, but the force is not exerted along dk, but dpd and ek. Very important to note. In a real world machine, in a real world construction of a DC machine, that length matters. That length matters. So that is a single loop DC motor. So let's say it rotates. So that force creates a rotation. Let's say we pivot the middle, happen to apply a pivot. So a pivoting system like a bearing. Or let's summarize it like this. Let's say this loop has the ability to rotate around its center, right? Okay, its center axis. So this force is going to, so if we have equal and opposite forces acting across a certain distance, that's what we call torque, right? That's what we call torque. We've seen that if we flip the polarity, we flip the force direction or the direction of rotation. Very, very important. So now what if we want to have a continuous kind of motion? What do? So we make some modifications. We make modifications, right, construction modifications. If we are to make modifications to the loop, we need to add what we call split ring commutators and brushes, so as to have the current in the same direction every time the loop rotates around. So every time the loop rotates, we must have the same direction orientation so that we have useful rotational motion. So in the next lecture, let's look at the generator action with a single loop generator. Then in the other lecture, we will look at the real-world construction of a DC motor, real-world construction of a DC generator. Then start off from there with the EMF equations and other parameters. Thank you.